terms you guys have to know about adding or about matrices in general. One is to make sure your screen can move correctly. Cool. All right, so I'm going to give you guys just a basic matrix. All right, I'm going to give you guys a number, any number called x, and that's going to rest on the outside. And I'm going to draw this big bracket box right here. And inside these brackets will go numbers, random numbers, like say A, B, C. That meaning they can be any number they want. D, E, and F. There are a couple of things you guys need to know about how this thing works. A row in a matrix, and this is where people tend to get mixed up. A row is the thing that moves side to side. Okay? A column is the thing that moves top to bottom. We always label our matrices. A matrix label will always be row by column. So in this case, this matrix here, no, okay, I'm about to lose some of you guys, is what we call 2 by 3. Raise your hands if I've lost you. 2 rows, right? 2 rows, 1 row, 2 rows. 3 columns, 1 column, 2 column, 3 columns. Raise your hands if you have any questions so far. Good? Brianna? Okay, row by column, so a 2 by 3 matrix. So if I was to give you something like, oh, I'm sorry, I need to identify x. I'll do that in a second. If I was to give you something like, say, 3, 4, 5, can someone raise their hand and tell us how can I name that matrix right there? Ty? 1 by 3? Do we agree? Jacob? 3 by 1 is correct. Because, Ty, there are 1, 2, 3 rows by 1 column. Okay? So you guys have to get used to that. That's one of the most difficult things to get used to in a matrix. Let me give you guys something really easy. 2, 4, 7, 9. What is that? That should be easy, a 2 by 2. Okay? So you guys need to make sure that you guys get your rows and columns straight. That's going to matter more in tomorrow's lesson, being able to tell your rows and your columns apart. This x sitting on the outside here, this is what we call a scalar. Just a number hanging out on the outside. That's all we call it. It's a scalar. So how does a scalar and a matrix interact with each other? Let's find out. If I have a scalar, and it's being on the outside of, say, A, B, C, C, and D, what that does, imagine a very, very big distributive property. Boom, 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 and boom. So what I get is x times A, x times B, x times C, and x times D. All right? So let's give ourselves a real-life example of this. If I was to say number 1 here, if I say 2 times, let's say 4, negative 9, 14, and 6. Who can raise their hand and tell us what is the resulting matrix from the scalar times the matrix? Chris, give us the top 2, please.
On the left,
8 and negative 18. Yes? Because we just distributed here. The bottom 2, Soph, can you give us the bottom 2, please? 28 and 12. Easy enough? Yeah. Multiply a matrix by a scalar. Piece of cake. I'm going to give you guys one to do on your own here. Number 2, 5, negative 6, negative 3, 1. Whoops, not 31. 1, 2, 12, negative 8. I want you guys to tell me what the matrix is and then label the matrix. So tell me what its dimensions are. Whoa, wrong pen. Okay. What are my numbers? What are my numbers? Miss Flynn, what are my numbers?
Negative 30, negative 15, 5,
Uh-huh. Uh-huh. Good. Let's see here. Wally, what's the dimensions of this matrix? 2 by 3. Correct. Raise your hands if you got both of those correct. Piece of cake, right? Cool. So what this is, doing matrix operations. There's only a couple more things you guys really need to know. You're going to be asked to solve an equation inside of a matrix, all right? And it's actually very easy to do. What I'm going to do is I'm going to give you a matrix here. So solving for variables in the matrix. Okay? Does not involve dodging bullets. Does not involve flying through the air and grabbing telephone poles and killing people with it. All right? It's a good movie, by the way. Matrix. All right. I'm going to give you a matrix here. Example 1. 2a, 3b, negative 5c, and 4d. And I'm going to say that equals 12, 48, 13, and 6. Solving variables inside of a matrix is very easy. You solve by association. So, 2a, what is its symmetric buddy, I guess, for lack of a better term? What is its symmetric buddy on the right side matrix? Nate? 12. Therefore, if 2a is symmetrical with 12, that means that 2a equals 12. Okay? 3b, what is 3b's buddy on the other side? Saida? 48. So would it make sense to say 3b equals 48? Yeah. Negative 5c, what is its buddy? Jack? Negative 5c is going to equal 13. Good. And then the last one, 4d, is buddies with 6. All right? So, you guys tell me. A equals, B equals, C equals, D equals. What do we got? Dustin? Uh-huh. 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 3 halves. Yeah, good. Reduce it. All right? We good so far? The one thing that I want you guys to take from this is that this here is one term, right? This is one term, this is one term, this is one term. Right? They're all separate. Unlike the next example when I show you what they look like when they're linked together. If I give you something like in example 2 here, x plus 3y and then 3x plus y, and I say that equals negative 13 and 1, one thing I want you guys to know is that because these are being added together, this is really one thing. One term here. So, when I solve for this, this is really x plus 3y equals negative 13, 3x plus y equals 1. So, the plus in between links them together and makes them one term inside the matrix. Does that make sense, everyone? Chris? Lauren? Okay. So now we are back in a position where we know how to solve this thing. I'm going to go ahead and multiply the top by negative 3. So I get negative 3x minus 9y equals 39. That's going to go away. I get negative 5y equals 40. Y equals negative 8. I plug it back into one of these. I'll choose the top one. So x plus 3 times negative 8 equals negative 13. So this is negative 24. X equals, if I add 24 to both sides, negative 23 plus, I'm sorry, negative 13 plus 24 is 11. All right? Raise your hands if you have any questions about this. Yeah, Gabby.
So basically you're setting up the two problems and you're putting it in the system and you're solving for them.
That's all you're doing, yeah. And in this case, you had to do it this way because the associative pairs are 1 to 1. Unlike this one, see how there's nothing linking them together? This is 1 to 1 and then 1 to 1. You know what I mean?
Yeah.
Okay, Dustin. Did I?
But you get 5.
Should be negative.
Should be 8y.
Oh, just kidding. So, boom, boom. This should be 5, right? Negative 5, which means x should be what? So let me redo this. X plus 3 times negative 5 equals negative 13. X minus 15 equals negative 13. So x equals 2. Sorry, so 2 negative 5. Sorry about that. I'm losing it. Yes, Max. Why did I multiply by negative 3? Because I needed to get rid of the x. Right? In order to get rid of the x, they had to match. All right? Okay. So let's do, let me give you guys one of these to do on your own. Okay. So how about we go with something like, say, 3x, 4y, z, and 6 equals 9. Actually, yeah, 9, 24, 8, and w. Solve for all the variables, please. Wally, what'd you get?
X equals 3.
Okay. Very good. Raise your hands if you agree with Wally. You should, because he's right. Good. Okay. We have to move on adding and subtracting matrices. Again, piece of cake. There's only one rule that you really need to follow with adding and subtracting a matrix. And I'm going to actually type this in. In order to add or subtract two matrices, the dimensions must be the same. All right? So, I will give you an example of that. 1. 3, negative 9, 4, 2, plus, say, 5, 7, 11, negative 1. Okay, we've got a 2 by 2 here, right? We've got a 2 by 2 here, which means we can add them. They are identical. So, I add by association. 3 plus 5 becomes 8. Negative 9 plus 7 becomes negative 2. 4 plus 11 becomes 15. 2, whoa, sorry, I crossed over there, plus negative 1 is 1. Questions on adding and subtracting matrices? Jack? Okay, sorry. Thought I saw your hand up. Oh, what do you know? Number 2 is written out there for me. Cool. Oh, sorry. Good? All right. The only way they can really make this harder would be if they did, say, 4 on the outside, and then, say, 2, 7, negative 3, and 6, plus 2, and say they gave you 1, 9, 3, negative 12. But we all know how to deal with a scalar on the outside. My new matrix on the inside here is going to be 8, 28, negative 12, and 24. Plus, my new matrix on the right side is going to be 2, 18, 6, negative 24. So who can raise their hand and give us the final matrix? What is the final matrix going to be? Basil, what do you got?
I got 10, 46, -6.
Raise your hands if you agree with Basil. Good. Piece of cake, right? It only gets really tricky sometimes when you're doing subtraction of matrices. And so just be really, really careful. Let me give you guys an example here. Example 3. If I give you a matrix that's, say, 4, -1, 3, 2, 7, -11, minus 2, 9, -4, -3, 6, and -14. All right. Be very careful here. This is 4 minus 2, well, duh, that's 2. -1 minus 9, well, duh, that's -10. 3 minus -4. 3 minus -4 is, Jacob? 7. All right, so please make sure you are being very careful with how you manage your negatives. 2 minus -3 is going to give me +5. 7 minus 6 is 1. -11 minus -14. Saida, 3. This is your final matrix. So please be very careful when you are when you're subtracting the matrices. Gabby. And then turn it positive. You could have done this, and then boom, 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 boom. Yep, no problem. Okay? Questions on matrices? All right, good job.